folks, welcome to 6.1. We are going to be talking about graphs of sine and cosine in this video. So let's start with what we know, all right? And we're going to go all the way back to what it means to be sine and cosine and tangent, all right? And one of the things that we might remember is that sine is a ratio of two side lengths of a right triangle, and it is in fact the ratio of the opposite side to the hypotenuse. And so if we divide these two sides, we get a ratio. That ratio we call sine. Similarly, cosine, I didn't leave myself enough space, but I'll write it over here. Cosine is also the ratio of two side lengths, but this time is not opposite over hypotenuse, but rather adjacent over hypotenuse. Lastly, tangent is also a ratio of two sides in a right triangle, and the tangent is actually the ratio of the opposite over the adjacent, right? And so we might remember these from our chapter 5 review that we call these SOHCAHTOA. SOHCAHTOA, as a way of remembering what those ratios are. Okay. And I've also put a little clip of the unit circle down here because that is something that we will find super, super helpful for our graphs, but also for this entire chapter. Okay. All right, moving on to what's new. So what does the graph of sine look like? That's going to be one question that we explore today. And how does it relate to the unit circle? We're going to ask ourselves a similar question, but about cosine. And then we're going to talk about some new characteristics that are important to graphs, all right? Some of these are new, some of these are ones we've seen before. Domain and range probably look familiar, all right? We're going to keep talking about those, but some newer ones we're going to bring into the picture are amplitude, period, and wavelength, all right? And last but not least, we're going to focus on our graph transformations for sine and cosine. All right, so let's begin. In this first part, we're going to talk about the graph of sine, what the characteristics of it are and where it comes from. Okay, and so I've done us a little favor. I've gone on Desmos and I've gone ahead and graphed sine. All right, and it turns out when you go into Desmos and you graph sine, you're going to get something like this. All right, it's sort of a wave, if you will. And what this graph doesn't show, because it's just a screenshot, is that this wave continues on the right-hand side, but it also continues on the left-hand side, okay? And so what that might tell us is that our domain here is all real numbers, but we want to make sure we're writing that in interval notation. So from -infinity to infinity, okay? Now, believe it or not, we typically tend to count in pi's here, just because it turns out that the graph ends up being a little bit nicer, okay? But it doesn't have to be that way. We could count by regular numbers as well. Now, even though the domain goes forever and ever in both directions, one thing that we might notice is that our range is actually restricted, meaning I see a maximum point and a minimum point, and then the graph just sort of travels in between these two. And we can see here that the lowest y value is -1, and our highest y value is +1. And so when we say our range, we're going to say bracket, -1, +1, bracket. All right, and we want to make sure to use brackets because we're including those values at -1 and at 1. All right, even, odd, or neither. And so way back in chapter 1, we talked a little bit about whether functions were even, odd, or neither. And when we're talking about things that are even, we would expect to see a perfect reflection across the y-axis. But if I take this point, it doesn't end up here, right? I don't see that perfect reflection. So this function, sine, is not even, okay? Now, is it odd? That should be the other question that we ask ourselves. And if you remember, odd functions are reflected not just over the y, but also over the x, meaning we sort of do like two reflections. That means that this point would reflect to here and then end up down here. And it sure does, right? So because this point gets reflected to this, or can be reflected to hit this point, we say that this function is odd, right? Sine is an odd function. All right, last but not least, let's talk about this new word, period, right? So period is really saying, answering this question. How many units does it take to complete one wave? All right, so the answer to this question, how many units does it take to complete one wave, will be our period. All right, so maybe we should go back to our graph and define what period or what a wave means. Okay, so a wave isn't just like this. Okay, a wave is also not just this, but a wave has to have all of the y values there. So if we were to start here, we'd go up, we'd come all the way back down, and then we got to get back to where we started. That's considered one wave. Okay, let me see if I can draw another or highlight another wave. So if I started here, I could go down, come back up, and get back to where I started. That's one wave. All right. Now I'm going to do this one last time, and I think this time it might be a little bit more obvious why. But if I start here and I go up and I come down and I go back up, that's one wave. And let's think about where we started. We started at 0 and we ended at 2 pi. So that means that one wavelength, or one wave rather, happens in 2 pi, right? So what does that mean? That means our period for sine is 2 pi. All right. So we've talked about domain, range. We know that it's odd and that it has a period of 2 pi. But where does this graph come from? Right? That's an important thing for us to ask ourselves is, sure, someone can give us the formula or a graph, but we kind of want to know where things come from. Okay, so we're going to actually use our unit circle values to help us plot a graph. All right, so I'm going to take this theta column. All right, you notice I put 0 in here, and I'm going to have pi over 2, pi, 3 pi over 2, and 2 pi. And then I also want to go in the negative direction to make sure that I've got a pretty good looking graph. So negative pi over 2, negative pi, negative 3 pi over 2, negative 2 pi. And if I go back to my unit circle, and at each one of these angles, I fill in the sine value, the y value on the unit circle, here's what I'll get. I'll get 0, 1, 0, negative 1, 0. If I go one way around the unit circle, but if I go in the negative direction, I'll actually get the following. Negative 1, 0, 1, 0. And now I'm going to plot these points. Negative 2 pi, comma 0. Negative 3 pi over 2, 1. negative pi 0, negative pi over 2, negative 1, 0, 0, pi over 2, 1, pi comma 0, 3 pi over 2 comma negative 1, and 2 pi comma 0. And then I don't want to connect these with straight lines, okay? Because there's actually a lot of other values in between here that we didn't graph, but instead I'm going to connect it with a nice smooth curve. We should end up with something more along the lines of this. Okay. And so even though the Desmos version is probably a little bit more perfect than mine, if you take a look at those two, the red one and the blue one, you can see that we basically end up with the same picture. Okay, so where does the graph come from? The short answer is it comes from the unit circle, all the values from the unit circle. All right, my friends, we're going to stop here for right now. All right, and then in part 2, we'll actually take a look at the graph transformation. So I'll see you back here.